In this video, we're going to derive some design equations for pi and t matching networks through a far-ranging set of series to parallel transforms. I've drawn our pi matching network at the top of this slide, and I've added a reminder that L1 and L2 add up to L, which is the component value that's actually in our circuit. We start by splitting our pi network into two L matches, as in the last video, but we make a kind of surprising decision with the left matching network over here. Instead of imagining that we're matching from Ri to Z0, as you might expect us to do, we're going to imagine instead that we're matching our source Z0 to Ri in the middle of our network. Meaning that we draw our port on the right of the L match instead of on the left, and our load on the left instead of on the right. I've performed the parallel to series transformations for each of our L matches on this slide. These two transformations each define a Q desired for the L match network in the same way that we've seen before. However, we're going to add an additional definition of Q desired that will be important when we try to figure out the overall Q of these two interacting L matches. We define the series L and C on both sides to be some reactance, x1 or x2, which means that each L match looks like an individual component. It's a resistance in series with some reactance. That means we can specify a component Q for each L match as either x1 over Ri or x2 over Ri. So now we have two different expressions that both equal Q desired. I've left off the equations for transforming the capacitors from parallel to series, but that should be done as normal. Also as normal, if the Q desired values are high, then CS is about the same as CP. Next, we bring the two parallel to series converted L matches together to represent the whole pi network. We can try to define an overall Q for this network, and we're going to do that by treating this like a component Q, like we did on the previous slide. First, we notice that the two reactances x1 and x2 are in series, which means that we can combine them into a net reactance x1 plus x2. The two terminals of the compound reactance are connected by two series Ri resistors. So the effective component resistance is 2 Ri. Therefore, the component Q is given by the compound reactance divided by the compound resistance, because this is a series component. So we find that it's x1 plus x2 divided by 2 Ri. This expression can be rewritten in terms of Q desired 1 and Q desired 2 from the last slide, which reveals that our overall Q is the average of Q desired 1 and Q desired 2. We can also find the natural frequency now that this looks like a big series RLC network. Both the inductors and the capacitors combine in series to give us an effective L and C, which we plug into our standard equation for omega naught. And we find that the total L sees the parallel combination of C1s and C2s when we're calculating our frequency. Now that we have these equations, we can work on flipping them around to turn design parameters into L and C values. Unfortunately, doing so is a mess, so I'm going to gesture in the direction of design equations, but I'm not ever going to expect you to design a pi or a t network with hand analysis. These are great problems for computers, and they're pretty joyless ones for humans. But at any rate, we start by picking our desired Q, which is the great affordance that a pi network grants us. And then by substituting in our equations for Q desired into the overall Q formula, we find that Ri is a function of Q overall, which is captured in this relationship. It's a messy function that I'm not going to invert here, but Ri does uniquely specify Q overall, or Q overall does uniquely specify Ri, which means that we can go from the Q we picked to an Ri value. Once we have Ri, we can find a component Q for each of the L matches in order to calculate the values for C1s and C2s. Note that we calculate Q desired 1 and Q desired 2 in these equations using Ri, and also note that we know omega naught because it's a design input, and we picked that. Finally, we use the natural frequency to find the value of L. I've omitted transforming the series compared capacitors back into parallel capacitors, but you have to do that too. Like L matches, this set of design equations isn't generic for every pi or t match. and you instead have to make some modifications for matches that use series to parallel transforms instead of parallel to series transforms. However, these are the basic design steps regardless of which match you use. You find your compound Q, then you go from Q to Ri, then you go from Ri to reactance values using the component Qs of each L match, and finally you use your component values in the natural frequency to pin down the last remaining component value. So in summary, we analyze pi and T matches by breaking them into two L matches, by matching Z0 to Ri and Rp to Ri to wind up with a big series RLC. In our example, you might wind up with a big parallel RLC in yours, or in some other network. And then you find Q desired for each match separately, and Q overall as a function of the two values of Q desired. Then you can calculate L and C values for pi or T matches by picking Q desired and using it to find Ri, finding CS1 and CS2 using component Qs and Ri, finding L using omega naught, and making sure to do it with a computer because it's pretty complicated to do by hand.